This is FRQ 6. So this is kind of a challenging problem. I would think this would be a time-consuming problem. So we're given a function, and we're given that we have it goes through the origin, and its derivative is an absolute value. Okay, and so that's going to be tricky. What I did is I graphed the derivative. And whenever you're dealing with derivatives and absolute values, it's best to break it up into a piecewise function. Okay, on the right, the derivative is 2x. On the left, negative 2x. And at x equals 0, the derivative is 0. Okay, and so what they're asking us to do is find expressions. Let's do it one at a time for g of x. So the antiderivative of this. Okay, and then note their solution breaks that up just like we broke it up into pieces. Okay, so the antiderivative of 2x on the right is x squared, and the antiderivative of negative 2x on the left is negative x squared. Okay, and then the antiderivative, if we were to graph the antiderivative, okay, on the right it's x squared. On the left it's negative x squared. Okay, and since this is the derivative, and the derivative has a value here, okay, the derivative is continuous, and so we have to have a point where these two curves meet. And that's why we have to include that the antiderivative at 0 is 0. Okay, and then part 2 of that problem is find the derivative of this, so the second derivative of g. Okay, and note their work. Okay, the second derivative is the derivative of these parts, and so on the right the derivative is 2, on the left it's negative 2, and then note that the slopes aren't approaching the same value at 0, and so this doesn't have a second derivative at x equals 0. Part B. Find the x-coordinate of a point of inflection of the graph of y equals g of x. Okay, so we have to remember what a point of inflection is. It's where concavity is changing. Okay, and there's a second part to that. We have to have either a second derivative that is 0 or is undefined. Okay, and so we just look at our solution here. Here on the left, my curve is concave down. Here on the right, my curve is concave up. And at x equals 0, okay, I don't have a second derivative there, it's undefined. And so I do get this concavity change at x equals 0. And let's look at their wording. The only point of inflection of g of x, and here I have a tiny little picture of that right here. This point of inflection at x equals 0, it's due to the concavity changing, g double prime changing from negative to positive. Note that they didn't include that the second derivative doesn't exist there. I would put it. Part C. Okay, and so we have a function that seems like it's unrelated, but we'll see why this is clearly related to the original function. H is the integral from 0 to x of this function. And like I said, it looks unrelated until we read what they're telling us it is. It's an arc length. And if you remember your arc length formula, okay, L is the integral from a to b, and then we have f prime of x, that all squared inside here, dx. And so if we look, it tells us it's the length of graph g. Well, we found earlier that, and this is on the right from 0 to x, when x is greater than or equal to 0. So our function right there is g of x equals x squared. Its derivative on the right is 2x. And when we look at what they're giving us here, where is part C? Okay, this right here is the 2x all being squared, the derivative being squared. So that is an arc length formula for G. Okay, and then they want us to use Euler's method. Starting at x equals 0, 2 steps to approximate h of 4. Okay, so remember what you're doing when you use Euler's method. And here I wrote a reminder. You don't have to memorize it. You guys know point slope form. All you do is you bring y sub 0 over. Your slope is the derivative, and this is your change in x. So what we're given is we're going to have some starting point, and let's find that before I actually start showing you what this means. Okay, your starting point is at x equals 0. That's 0 right here, and the integral from 0 to 0 is just 0. There's no area under that curve. And so your starting point is the origin, okay, and you want to take 2 steps to approximate h of 4. And what we're doing is we're saying, okay, I'm going to plug in 0 here for y. I'm going to find the slope there, and we'll do that in a second. And then the change in x, well, since I'm making 2 steps to get out to x equals 4, my change in x is going to be 2. So I go here, find a point, go again here, find another point. That's what Euler's method is doing. And let's look at their work now. Okay, so we evaluated h of 0. We discovered it's 0. Okay. Note, I guess the first thing that they did is they used the fundamental theorem. We have to find the slope for this part of Euler's method right here. We need the slope of our function. And so if this is our function, its derivative is the derivative of this integral, and that's the fundamental theorem. This is appearing many times on these problems. Okay, and so the fundamental theorem, okay, the derivative of the integral, they're inverses, and so here I have the equation for my slope of the curve. Okay, and I can evaluate it for the points, and the first point I'm using is 0, 0. And so the slope there, put a 0 in for x, I get 1. Here's your delta x. And so what this tells you is that your first approximation using Euler's method is the original y value, the slope times that change in x, which is 2. That means 2 comma 2 would be the point we would use next, 2, 2. Okay, and then to find this one, you just use 2 for x, 2 for y, and you need to do the same thing. So note that h of 2 is that 2 we just found. Okay, and then our delta x is still 2, and the h prime of 2 is what we would get if we put a 2 in for x. Okay, and we just leave it. We don't use our calculator to approximate that. Okay, and that's how we find h of 4 approximately using Euler's method. And then part D. Okay, find the value from pi over 2 to pi. Note the positive numbers of this. And so we have to go back and to an earlier part. I guess I'll look at my graph. So when x is positive, g prime was 2x. And so this really they should have just written 2x cosine x dx. Okay, and that to me looks like fairly straightforward. Here, I'm going to write it on here. So we're doing the integral from pi over 2 to pi of 2x cosine x dx. Looks like a pretty straightforward integration by parts problem. Okay, and so I have to find u. You could use tabular for this if you wanted to. And I have to find dv. U dv, and then I find du. Don't forget your differential. I find the antiderivative of this, and here's my box. We always made those sideways rectangles. And so this integral, I guess I could have read, I didn't see it here, is just uv minus v du. Okay, and they simplified it a bit there. And note they included the limits here. They didn't touch this on the first step. They anti-derived that. And then they just use the fundamental theorem part 2 to evaluate upper limit minus lower limit on both parts. And note your points.